Welcome to The Explainer. Today, we're going to pull back the curtain on software security. And look, this isn't just about firewalls and antivirus software. We're talking about a hidden, high-stakes battle being fought deep inside the code that runs our world. It's this constant, fascinating cat-and-mouse game between attackers and defenders. So let's just start with the big question, right? We trust software with literally everything, our money, our secrets, our photos. But why does it all feel so breakable? Why are we always hearing about some new, massive security breach? What gives? Well, the answer is kind of funny. It's both incredibly simple and ridiculously complex. But more often than not, it all boils down to one single tiny flaw, a microscopic mistake buried in millions of lines of code. And today, we're going to follow one of those tiny mistakes and see just how it can bring a whole system crashing down. All right, let's dive right in with what you could call the original sin of software security. It's a classic heist, and it's known as the buffer overflow. Seriously, if you can wrap your head around this one vulnerability, you'll understand the entire arms race that follows. So what is it really? Well, in a computer's memory, a buffer is just a little temporary storage spot, kind of like a box that's built to hold a specific amount of stuff. A buffer overflow is exactly what it sounds like. It's what happens when a program tries to stuff way too much data into that box. The best analogy is right there. It's like pouring a whole gallon of water into a tiny coffee cup. The water doesn't just stop at the rim, right? It spills everywhere. Let me walk you through how this hijack actually goes down. Okay, step 1, a totally normal program asks for your name. Easy enough. Step 2, an attacker, instead of just giving a name, provides a super long string of data, and hidden inside that data is malicious code. Now, step 3 is where the chaos begins. All that extra data overflows the buffer and starts spilling into adjacent parts of memory. And this is the key. It overwrites the program's return address. Think of that as a little sticky note telling the program where to go next. Instead of pointing back to a safe spot, it now points directly at the attacker's hidden code. And that takes us to the final step, the hijack. The program, just trying to follow directions, jumps to that malicious address, and boom, game over. The attacker is now in control. And you might think this is some rare, super complex mistake, but nope. It's actually rooted in some of the most common and powerful programming languages, like C and Z++. You see, certain functions in these languages, like the notorious stcopy, were built for one thing: pure, raw speed. They just copy data from point A to point B, and they never, ever stop to check if it's going to fit. It's like a factory robot that's told to put 20 things in a box that only holds 10. It doesn't care. It just keeps piling them on, letting them spill all over the floor. It's a perfect storm for an attacker. So, as you can imagine, for years, attackers had an absolute field day with this. But the defenders, they thought back. And their first big countermove was honestly brilliant in its simplicity. They basically said, okay, if attackers are sneaking code into our data areas, let's just build a wall. And they called this wall non-executable memory, or NX for short. Here's how it works. Modern computer processors can literally mark certain regions of memory as data only. So a place like the stack, which is the program's scratchpad, gets this big data-only stamp. You can write data to it, you can read data from it, but you absolutely cannot run it like a command. So an attacker can still overflow the buffer, but the moment the program tries to jump to that malicious code, the processor itself steps in and says, no way, and just slams the door shut. Just like that, the classic hijack was stopped dead in its tracks. But of course, that wasn't the end of the story, not even close. Attackers are clever. They're persistent. If they couldn't bring their own weapons to the fight anymore, well, they just have to find another way. The game was about to evolve. And this right here is the big aha moment for the attackers. They had a realization. The program's own code, all the legitimate, trusted instructions, was already sitting there in memory that was marked as perfectly fine to execute. So it led to this huge shift in thinking. Why bother trying to sneak in your own army when you can just take command of the one that's already there? This new strategy has a pretty cool name: Return-Oriented Programming, or ROP. And this table just lays out the difference perfectly. Instead of injecting their own code, ROP attackers hunt for tiny, little snippets of existing code, they call them gadgets, that are already part of the program. Then they use that same buffer overflow not to inject code, but to write a new to-do list for the program, a chain of addresses pointing to one gadget after another. It is exactly like building a ransom note by cutting out individual words from a magazine. Each word on its own is harmless, but when you string them together in a new order, you get a malicious message. And the really genius part? Since it's all using the program's own trusted code, that big NX wall we just talked about becomes totally useless. So the attackers had adapted. The ball was back in the defender's court, and now they had to build even higher, even more complex walls. It was time to start building some serious digital fortresses. See, the whole problem with ROP is that it relies on a predictable map. An attacker can study a piece of software, find all those useful gadgets, and know exactly where they live in memory. So the defenders thought, okay, what if the map was different every single time? If the enemy is using your map against you, the best defense is to constantly redraw the map. And this defense is called Address Space Layout Randomization, or ASLR. The idea is just beautiful in its simplicity. Every single time a program starts up, ASLR completely shuffles its memory layout. Now, the early versions were only partial. They'd randomize some things but leave other key parts in the same place. Kind of like shuffling the house numbers on a street but leaving the street signs the same. Attackers could still figure it out. But full ASLR, man, that randomizes everything. The program itself, all its libraries, the stack, the heap, it all gets thrown into a blender. Suddenly, the attacker's carefully drawn treasure map is just worthless. But you're probably thinking, okay, but what if the attacker is really good and finds a way to leak some information and figure out the new map? Good question. Defenders needed another layer, and that's where control flow integrity, or CFI, comes in. Think of it like this. CFI is like a security guard with a super detailed blueprint of the program. Before the program even runs, CFI analyzes it and maps out every single valid path it's ever allowed to take. Then, while it's running, the guard watches every single move. If the program ever tries to make a jump that isn't on that pre-approved blueprint, like, say, to the beginning of an attacker's gadget chain, the alarm goes off and the whole thing gets shut down immediately. So now, defenders have this amazing toolkit, right? But it's not that simple. It creates a new challenge, a balancing act. On one hand, you have what's called toolchain hardening, things like NX and ASLR. They're basically freebies. You flip a switch when you compile your code, and you get this huge security boost with almost no hit to performance. Awesome. But on the other hand, you have these runtime defenses like CFI. They're like that constant security guard, offering incredibly powerful protection, but all of that checking and double checking can slow the program down. It's the classic endless engineering trade-off. Do you want maximum security or do you want maximum speed? You see the pattern here, right? It's this endless back and forth, a true arms race. Which brings us to probably the most important question for anyone out there who's actually building software. How do you stay safe in the middle of all this? Let's talk about the best practices that have come out of this long, hard-fought battle. And look, the big lesson here is that there is no single magic bullet. Modern security is all about defense in depth, having multiple layers. It starts at the very beginning with secure coding, which means not using those dangerous, unsafe functions we talked about. It means always using those toolchain hardening features like NX and ASLR. It means having other humans look at your code and using automated tools to scan for bugs. And critically, it means thinking about security from day one, planning for threats, and making sure every piece of your system only has the bare minimum permissions it needs to do its job. And all of that really boils down to this one absolutely critical idea. SDLC just stands for Software Development Lifecycle. The point is, security can't be an afterthought. It can't be some feature you try to bolt on at the very end. It has to be woven into the very fabric of how you build things, from the first sketch on a whiteboard all the way to the final release. So we've gone from a simple, overflowing coffee cup all the way to these incredibly sophisticated digital fortresses. We've seen how every time one side makes a move, the other is forced to innovate and evolve. This cat and mouse game, it never ever stops. Attackers are always looking for the next crack in the armor, and defenders are always trying to build it stronger. Which leaves us with one final hanging thought. In this perpetual digital arms race, who makes the next move?